Okay, so first a little history lesson. You're doing some advanced math. You need to appreciate some advanced mathematicians, and this guy is one of the kings here. Leonard Euler. All right, that's Euler pronounced Euler. Lived in the 1700s. All right. He was born in Basel, Switzerland. Maybe Basel, I actually don't know on that one. He is believed to be the greatest mathematician of the 18th century. He published 886 papers and books. He's also regarded as one of the most prolific mathematicians to have ever lived. Well, of course, he wrote a lot. All right, so who wants to try a little bit of reading here? Gracie, you tell us the where and the when. Euler, remember.
Euler was born and educated in Basel, Switzerland. Initially, he was taught mostly by his father and through independent study, which was guided in part by his father's friend, Johann Bernoulli. In 1727, age 20, Euler accepted the invitation from Catherine I to come to Russia, where he joined the St. Petersburg Academy of Sciences. The spot had been vacated by Nicholas Bernoulli. In 1733, age 26, he advanced to the senior chair of mathematics at that institution. The spot was vacated by Daniel Bernoulli.
Yeah, Bernoulli's kind of also another big name when it comes to...
Okay, I was like, are we the same one? In 1741, age 34, he accepted the invitation from Frederick the Great to join the Berlin Academy of Science in Germany. He worked there for 25 years, until in 1766, at age 59, he returned to St. Petersburg, where he lived out the remaining 17 years of his life. He died in 1783 at age 76. He had married twice and had 13 children, but only 5 survived to adulthood. When Euler died, it took the St. Petersburg Academy nearly 50 more years to finish publishing the backlog of his unpublished works.
All right. That's Euler, remember, not Euler. Euler. Rigel, read about this blindness.
In his early 30s, Euler lost sight in one eye. Conflicting reports cite fever or eye strain from cartography work as the cause.
Map making is what cartography is. Keep going.
Soon the sight in his remaining eye began to fail, from similar causes and or a cataract. In his 50s, and for the remaining 2 decades of his life, he was totally blind. It is an amazing testament to his extraordinary memory that his blindness barely affected the progress of his work. He produced almost half of his total works while blind.
Like, what? He wrote all these, it took another 75 or 50 years to publish his stuff, and he was blind for the last more than quarter of his life? All right, let's read it. Arlie, read up to us about his legendary calculation and concentration skills.
Okay.
Euler, remember.
Euler could recite the entire
Aeneid,
a 12-book epic poem of the history of an ancient Rome, word for word. Interruptions and distractions did not interfere with his work. He could play with his children and work out
computations
in his head simultaneously. A story is told of 2 of Euler's students, such having some 17 terms of complicated infinite series, but disagreeing in the 50th decimal place. Euler settled the dispute by recomputing.
recomputing.
You guys are good at reading. The sum in his head. Francis?
Sure. I think it's supposed to be Francois.
Said of him, he calculated just as men breathe.
Yep. Alright, so let's see what he accomplished. Euler contributed enormously to number theory. He proved that E was irrational. By the way, E for Euler, yeah. Found the sum of infinite series, proved many of Fermat's assertions. Algebra, modern analytic geometry, differential geometry, logarithms, complex numbers, trigonometry. He was the first to consider sine, cosine, etc. as functions rather than as chords. Analysis, analytic functions of complex variables, topology, the Bridges of Königsberg problem, differential calculus, analytical mechanics, fluid mechanics, optics, electricity, magnetism, hydrodynamics, hydrostatics, elasticity, acoustics, wave theory of light, astronomy, celestial mechanics and lunar theory, music theory, cartography, artillery and ballistics, shipbuilding, navigation. Anyway, here are just a few of those notations that Euler coined. He was the one who started using it, and then all mathematicians followed. F of x. E, I, pi, sigma for summation, and delta. You're like, what the heck? This guy is like,
That's all we use.
it's him and Newton. I mean, that's it. Yeah, these are the kings. There are so many Euler constants, Euler numbers, Euler angles, Euler theorems, Euler formulas, etc., that each may refer to a different idea depending on the context. Absolutely true. There's an Euler's theorem for like geometry. There's an Euler's theorem for trigonometry. There's an Euler's method for this. Anyway, just a few of those encountered in high school math up here below. So the faces plus vertices equals the edges plus 2. That's a geometry Euler's formula. Then e to the I pi plus 1 equals 0. That's complex numbers, as well as e to the I theta cosine theta plus I sine theta. Natural log of -1 is pi I. And he won the Paris Academy Prize 12 times. So there's some sources on that. Anyway, I mean, unbelievable, right? That is pretty amazing what he was able to do. And so today we are going to talk about another one of Euler's contribution, and that is Euler's method for computing a particular solution to a differential equation, and it's using the slope fields. Let's see if I can. I don't know if I'll be able to find it here. Oh, here we go. Let's go one at a time. All right. Why don't you go and read to us the instructions there?
For each problem, find a particular solution of the differential equation that satisfies the initial condition. You may use a graphing calculator to sketch the solution on the provided graph.
Okay. So, Gracie, I don't know if you looked at the slope field. Have you seen? Did you watch the video from yesterday?
No.
Probably not. Okay. Well, there's a slope field.
Alright.
All right. What this is if we look at this differential equation, okay, this is like this would be the derivative. If you take the antiderivative of that, it would be something like -2x squared over 2 plus 4x. Okay, so obviously this is linear. If this is the derivative, the original function would be, what type of a thing would it look like? Parabola, yeah. And it'd be negatives would be opening downward. Okay, so if we imagine what that would look like, it would probably look like something like this. But we would also have the plus c term, so it would look something also kind of like this, or another one that would look like this, or another one that would look like this.
It's almost like force lines.
Mm-hmm. So, yep. And if you were to do the local linearization, draw the little tangent line here, 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 and here, draw tangent lines here, draw tangent lines here, draw tangent lines there, then what we're looking at right now, if I erase all this, would be that diagram. It's a bunch of little line segments representing the slope of the tangent line of that family of general solutions, okay? Or there's maybe a snapshot of those different particular solutions, probably more specifically, okay? So, what Euler said is, he said, all right, well, and yesterday, Gracie, what we talked about is how to, if you're given this, how to build how to build that. So it's fun. Euler said, okay, we know that our official answer, the equation that we're looking for, has the coordinates 2, 3. So over 2, up 3. So that's the point that's going to sort of lock us in. Now, if we wanted to, at this point, sort of do a sketch, then we could do that. We could, I don't want you to sketch just yet, because we're going to go, we obviously know it's going to look something kind of like this and something kind of like that, right? But what Euler said is we can actually provide sort of, I mean, the question is like how how wide does it go? Does it go really wide, or does it go kind of narrow? Like, can we get some boundaries, on that curve? And he said, yeah, you actually can. So what you do is you go out a unit left or right depending on what that slope is. Okay, so for instance, let's just pretend that we don't know that slope is 0. Let's plug in 2 into our differential equation and figure out what slope we would get right here. Okay, so if we say what's dy over dx evaluated at the coordinate 2, 3. So we can plug in plug in 2, so -2 times 2 plus 4. That's going to be 0. So we have a slope of 0, and I'll kick out 0 this way. I'll also go out 0 this way, and I'll say, all right, this isn't necessarily a point that's going to be on my curve, but I know that my curve is going to be somewhere within this. All right. Now this coordinate right here is 3, 3. Let's go ahead and calculate the derivative at 3, 3. So my derivative equation is right here, so that's going to be -2 times 3 plus 4. So -6 plus 4, -2. So we'll do a slope, write that as fraction. That means -2 over 1. So down to 1, 2 over 1. Right there. I can't really go any farther in this direction, so now I'll go over here and let's plug in what the slope is at this point. Happens to be 1, 3. So dy over dx evaluated at the point 1, 3 is going to be -2 times 1 plus 4. So -2 plus 4, +2. Now I can write that as 2 over 1. If I go up 2 over 1, I'll put a part here. That doesn't seem right. What's another way that I can write 2 over 1? See what I'm saying? Like if I go up 2 and over 1, I'm going to put a dot right here, and I'm like that. I could write it as 1/2, but another way I could write it is -2 over -1. That's kind of what I was going for. All right, and that will give me a slope where I go down 2 and over 1. You see, that's the same. That'll give me that same line as if I were to go up 2 and to the right 1. And we just play this game until we hit the edge on either side. In this case, I'm still within the boundaries, so this is the coordinate 0, 1. So I'll do dy over dx evaluated at 0, 1. So that's going to be -2 times 0 plus 4. In these cases, the y value is not really playing a role, but in some of the homework problems, the y value does play a role in the differential equation. So anyway, that's 0 plus 4, so it's just going to be 4. As a slope, I could write that as 4 over 1. Once again, that would kick me up here to the right. What's another way I could write the slope of 4 over 1?
-4 over -1.
Yep. -4 over -1. So down 4. 1, 2, 3, 4, and over 1. Okay, so this is going to provide a bounding box, so to speak, for my particular solution to that differential equation. So I'm going to draw this, and if possible, I'm going to try to go here between the gates here. So I'm going to try to go kind of like that.
Wait, what are you drawing
Right now I'm going to draw the parabola.
Oh, okay.
Okay, but I'm going to try to draw it so that it's kind of flat up here. Now if I do, I'm going to make this a little bit flatter. Now, and I'm certainly not going to cross the red line. Okay, it's clearly within that boundary. And the general idea here to try to get this is to go in between some of these, not necessarily in the middle, but maybe we should have made it a little bit steeper than it might have. But you can kind of see, that's the official answer. I guess we need to find a particular solution. All right, so algebra, we sort of like graphed it, okay? Now, let's go ahead and algebraically, let's find out what the correct answer is. So I'm going to multiply both sides by dx, so we have negative 2x plus 4 times dx. So this is how we solved those equations before. If you remember, take the integral of it, so now we have y equals negative 2x squared over 2 plus 4x plus c. Now if you remember when we did this earlier, I put a plus c over, like plus c1 over there and a plus c2 over here, and then we all said, okay, subtract c1 from both sides and you end up with another constant. So when we have this sort of situation, I'm just going to put the y over there and then put the plus c in this case. And then we have those two that cancel out, so we have y equals negative x squared plus 4x plus c. I guess I should read the instructions because it does say find the particular solution to the differential equation, and then we're going to use Euler's method to graph it there. Okay. Now the particular solution, is this the particular solution?
It's general.
What's that?
Is it the general?
This is the general solution. You're correct. We're going to plug in 2 and 3 to figure out what our c value is. So here we have 3 for the y is equal to negative 2 squared plus 4 times 2 plus c. So 3 equals negative 4 plus 6. Nope. Negative 4 plus 8. So that's 3 equals 4 plus c. So negative 1 equals c. Oh no, I'm kind of doing this fast here. Does that seem about right to y'all?
Mm-hmm.
So our final answer, a particular solution, is going to be y equals negative x squared plus 4x minus 1. And we have the benefit of technology of being able to, just plug that into the calculator and then being able to get the graph. Back in Euler's day, 1700s, I mean, think about, what's going on. American Revolution, around the time that he died. That's a little technology was happening. So, math problems by candlelight if it's winter time. Eesh, there's a lot of problems there.
So what are you wanting us to do for each of these problems? Like find the particular solution.
I want you to find the particular solution using our differential techniques, which we've done before. I also want you, this method that we had here of sort of tracing it through is called Euler's method for finding the...
So you want us to do that part 2 to find the boundary?
Yep, find the boundaries and to sketch it. But I feel like 16 problems is kind of much. So let's go, I think odds are a pretty good one on this one. All right, any questions? Give you all some time, give you about 20 minutes to start making some progress on that.
When will this be due?
Probably Tuesday, I guess. We've got like 3 other things to do on Monday.
Okay, so I have a question on the one we did yesterday.
Yep.
I know how to do how we do all of those. How would I do this one with just
Okay, so what is this sentence telling you?
that
The derivative equals 9. Okay. So, so there's nothing to plug in, right?
yeah,
What's the derivative at the origin? No.
9,
9. What's the derivative here?
9,
Derivative here. 9, 9, 9, 9, 9, 9. Everything's 9. So just make that line. So
Oh, okay. Thank you.
Yep. Alright, thanks for watching.